In this session, I discussed how we can troubleshoot any switch mode power supply circuit, what are the checkpoints, and how we can fix it. I used this flowchart method. If these voltages are present at bridge rectifier, then we will continue to next. If no, what to do. I discussed all possible faults and their remedy. We will continue step by step. Let's start. Assalamu alaikum wa rahmatullahi wa barakatuhu. Friends, welcome back to my channel. In video number 1154, I repaired this power supply. It is UC3842 based SMPS. While troubleshooting process, I removed its switching module, that is switching IC and VCC capacitor and other related components for oscillation. Because there was no space, I removed this board and placed it in rear side. I tested the voltage. I found VCC voltage were present but no reference voltage. I replaced that IC. After installing the IC on this switching module, I inserted this module inside PCB. I did not check voltage again. Why? Because for removal, for installation of IC, I removed the board again. Soldering, desoldering, many times soldering, desoldering makes problems in the PCB. So when I install new IC, I am confident that this IC will work. So that is the reason I installed inside PCB. I tested, the output started working. Then there is no need to test voltage again. And I received comment from my viewers. First comment, how you recognize that this chip is damaged. When we not have feedback voltage, first we check resistors in feedback rail. But you first go to IC directly. Second question from my viewer, if reference voltage are missing, can we not inject external voltage? We will discuss it. Then I received many comments for viewers to provide checkpoints for any switch mode power supply. So in this video I will make a complete troubleshooting process step by step. I will use sample circuit for this 3842 IC. It is not exactly the same circuit, but it is a sample circuit, how 3842 IC works. When we are working on any board, any circuit, we must analyze the circuit so that we can take a logical approach to the circuit. If we discuss this circuit, line input here, fuse, might be there is some over voltage protection or frequency protection, any type of EMI, RFI, then the voltage will reach to bridge rectifier. Before this, AC voltage, then DC voltage here at this capacitor. As this complete board needs AC voltage to provide output power, exactly same, there is a portion that is this switching IC. It is a generator. It needs some power, that are VCC voltage. In this chip, we are providing VCC voltage using startup resistor. Might be in some circuits we are using some external power supply, similar way as we say standby power supply, that is generating some voltage that are required for that chip. If here we are using 2842, 3842, might be in other circuit 3845, 3846, TL494, 3525, 7500, any IC that will start switching that needs a power, that are called biasing voltage or VCC voltage. If that voltage are not provided at this pin due to any reason, this IC will never start. When it will receive VCC voltage, then this IC will start to produce reference voltage. It will create a fixed voltage reference to start fixed frequency oscillation. If the supply voltage are varying at reference pin, that IC cannot produce exactly fixed switching frequency. For that purpose, the reference voltage must be present. If these voltage are not present, this IC will not work. After that, this drive signal will reach here. There is soft start circuit, current feedback circuit, voltage feedback circuit. this transformer driver circuit, that is MOSFET and its related components, then we will receive output here in the secondary side. There is rectifier, capacitor. Here is voltage feedback circuit. When it will maintain output voltage, the voltage will be produced from here. Let's make a logical flow chart of this circuit. In the first step of troubleshooting, we check input voltage. 220 volt present, yes or no. If 220 volt are not present, what we do? We check cable, we check its connector, we check voltage on cable, then we check fuse. If everything is good, the voltage must reach here and we will receive voltage here again. If voltage are present here, then we will come to bridge rectifier inputs. Present or no? If present, then we will continue to next circuit. If not present, might be there is fuse, MOV, surge arrestor, any type of RFI, EMI circuit, any type of thermistor. After fixing this stage, we will return back here. If 220 volt present now, then we will reach here. Now if 220 volt are present at bridge rectifier, voltage value 220 volt RMS, we will check DC output. DC voltage on bridge rectifier here. AC input multiply with 1.414. If 220 volt, multiply it with 1.414. Is the voltage value on capacitor is same to this value AC RMS which we tested here at input. And what are the output? If you are 220 volt, 220 multiply with 1.414, 311 volt. Yes or no? If yes, then we will continue to next. If no, might be smoothing capacitor is not good. If this capacitor is open circuit, that time it will not hold the charge. If this capacitor is open circuit or it is leak, it will not allow to build same voltage value, that is 220 multiply with this number. Basically it is RMS to peak converter. Might be smoothing capacitor is bad, or maybe bridge rectifier is working as a half wave rectifier. Pair or one diode is open circuit. If it is short circuit, it will make another problem. If any one diode from these 4 diodes open circuit, that time the voltage value will drop on this capacitor. After this we will return back here. Another problem, if fuse is blowing again and again, then these items plus MOSFET and these items, and then we will return back. If MOSFET is short circuit, if smoothing capacitor is short circuit inside, it will cause to damage the fuse. MOSFET is damaged, it will blow the fuse again and again. In addition to these components, MOV, surge arrestor, class X capacitor, class Y capacitor, like that. DC rail stable, yes or no? If the DC voltage on DC rail at this capacitor are stable, then we will move to next stage, next troubleshooting. If there is fluctuation, that is not due to these components, that is might be due to any other circuit that is involved in the switching. When these voltages are maintained, the next requirement is switching this IC. This IC must take start. Check VCC voltage. To test VCC voltage, we need to check datasheet for this IC. What are the startup voltage? Let's suppose this IC will start at 16 volt for initial startup. In this case 16 volt 3842. If the voltage are present, we will move to next. If not present, what to do? Might be this startup resistor, that is current limit resistor, that is charging this capacitor, because this time auxiliary voltage are silent. We will receive voltage from this line. Maybe our startup is bad. If resistor is good, this capacitor is short circuit internally. If VCC capacitor is short circuit internally, it will discharge this voltage here in the ground, in the primary ground. So there will no voltage on this capacitor. If bias diode or VCC diode or auxiliary voltage diode is bad, this one, it is short circuited. Voltage from this line will reach to ground through this auxiliary winding. Then there is clamping diode, voltage clamp. Most of the time 18 volt clamp is connected at pin number 7 to protect this IC from damage. If this diode is short circuited, Zener diode is short circuited, it will also be a cause to not allow charging to this capacitor. Then there is next reason, that this IC is damaged. If we don't have voltage on this capacitor or pin number 7 of this IC, that time this IC will never take start. First we need to verify voltage on pin number 7. If we find the reason, then we will return back to start over from here, from the first page, the same flow chart. If voltage are present, stable or not. If the voltage are not stable, these are varying, this will indicate that IC is starting, but there is no feedback. Feedback is missing. That is this feedback. We will discuss this in upcoming segment. And if voltage are stable, then we will check reference voltage, that are 5 volt. This IC will receive voltage from this capacitor. There is internal reference circuit, that is 5 volt regulator, that will provide a fixed reference voltage to its error amplifiers, to its RTCT circuit, that is oscillator circuit, to provide fixed frequency, and chip biasing for its internal components, for its flip-flops, for drivers, for its comparators. Everything will receive power from this V reference. Might be its regulator is good. Any one component other than regulator is damaged. That is drawing the current from this line, from the reference line. This IC will not work. And we cannot inject external 5 volt. If not present, might be its CSS, soft start capacitor, or its soft start circuit is bad, soft start capacitor is bad. This IC will not work because it will discharge these 5 volt. Might be CV reference is bad, that is 5 volt reference capacitor. If this capacitor is short circuit, it will not maintain reference voltage, so this IC will not take start. Might be its RC oscillator, its capacitor is damaged, or any external component that is here, or maybe any protection circuit is enabled, that will disable the function of this IC. If these parameters are okay, this IC must take start. If it is not starting, that means this IC is bad. Most of the time these first parameters are good. The most problematic component is IC, and then we will return back. If IC is bad, we will replace and we will check the circuit again. If reference voltage are present, then we can check oscillator, drive signal, ramp signal here. At pin number 4, most of the time I never check ramp signal, because if IC is good, it will provide output here. If IC is bad, it will not take start. If we have this oscillator signal, drive signal at pin number 4, ramp signal, that means the reference voltage and its internal block is working. If no, most of the time the IC is bad. Then it will provide PWM drive at pin number 6, that is here. If it is not providing, the most possible reason IC. Pin number 4 and 6. First we will check signal pin number 4 and ground, then pin number 6 and ground. Pin 2 is feedback, that is voltage feedback from here. If oscillator and drive signal is present, then check in secondary side voltage. Here we will check voltage across this diode, Schottky rectifier. In most cases, if this section is working good and we don't have output here, most of the time this rectifier is bad, this capacitor is bad, our feedback circuit is bad. V out, yes or no. In case we don't have voltage here, that time this MOSFET, that is drive circuit, its I-sense resistor, it is damaged, and transformer winding, transformer primary winding, then secondary winding, because when current will flow from here, it must provide voltage, and sometimes these gate drive components are bad. Gate drive components, this resistor, this IC, and sometimes there is clamp. Clamping diode at pin number 6 that protects this IC from negative spikes during switching. If anything out of these components is bad, we will not find output here. We will check voltage across this diode, DC voltage. Voltage across Schottky rectifier, this one, that is D out, present or no. Most of the time when this rectifier is short circuit, we will receive a few millivolts. This side will fluctuate and here we will not find any voltage, few millivolt, because that time it will create a short link. Might be diode, might be smoothing capacitor in the output side. After fixing, we will return back to start over to the point number 1. If we have voltage here, are these voltages regulated or no? If yes, we will continue to next step. If no, we need to check this diode, capacitor, feedback circuit, its TL431, optocoupler, reference circuit, that is for TL431, that is voltage divider network. If anything is bad, we will receive fluctuation here, and sometime we receive fluctuation from VCC capacitor. During initial startup, this capacitor will charge, but after startup, when this auxiliary winding will provide voltage here, it will not hold the charge properly, or after a few seconds or some minutes, this IC starts fluctuation. That is due to this capacitor. After finding the root cause, start from 0. When we have regulated output, then there are some other steps to be checked. Now we will go to datasheet and we will check VCC threshold. Suppose we need voltage between 16 volt and 8 volt. That means we will receive 16 volt in full load condition. This threshold will indicate what is the load size. When there is full load, that time we will receive 16 volt at pin number 7. At no load condition, we will receive approximately 8 volt, 9 volt in this window, depending on the input voltage. If voltage are from 8 volt to 10 volt, that is acceptable with no load condition. VCC threshold at no load. In limit or no. When we are providing 220 volt, that time the IC will utilize minimum duty cycle to run this transformer and its feedback circuit. If it is switching at more and more duty cycle with no load, when we will put load, that time will not have a spare headroom to turn on this MOSFET for long time. We need lower level threshold of this VCC voltage while working without any load. If not, that time we need to adjust our VCC. Most of the time this will fix the problem. If we will increase the resistor size, it will decrease the voltage at pin number 7 while providing voltage from here. If we are receiving more voltage here without load, when we will put load, for example, we are receiving 14 volt here at no load condition. Now just there is 2 volt space between overload protection. When we will put a small load, let's suppose this IC is for 70 watt, 0 watt lower level, 70 watt 16 volt at VCC pin. Now if you are receiving 14 volt without load, if I will put 10 watt load in the output, that time this IC will stop to work because it will reach in OLP, overload protection mode. Why? Because VCC voltage are in top limit. That time this IC will not drive full load or VCC resistor. Then start over. Then we can check duty cycle. Full load at minimum input. For example, we provide 110 volt to this IC and we will put 70 watt. That is the maximum capability of this circuit. That time it will provide maximum turn on time. If this IC is working without load in this region, for example, if no load, it is providing this duty cycle, might be it is, we can say 40%, maximum is 48%, 0% to 48%. If this IC is driving at 40% without load, there is a very limited space, that is just only 8% to handle the load. That time this circuit must be re-evaluated to provide minimum duty cycle. At no load, for example, this IC is working at 2% to 5%, that's good. When we will put load, that time this IC will handle the load, it will regulate the output. We need to verify minimum duty cycle with no load and maximum duty cycle with load. This test needs oscilloscope. If not, we need to check feedback circuit, that is this one. We need to check its compensation circuit, I sense pin. If we discuss 3842 ICs, 3843, 3844 ICs, anytime if the voltage peak will reach here at 1 volt, that time this IC will shift in leading edge blanking. That time this IC will work in current limit mode, constant current mode. We can say this is 1 volt, this is 0 volt. At no load, it must provide a few millivolt peaks. When medium load, we will receive 0.5 volt peak. At full load, we will receive these peaks. Anytime if this IC will receive above than 1 volt peak, it will skip its switching cycle. For example, at no load we are receiving this peak. That means this IC is utilizing more current to drive this circuit. Might be it is using minimum duty cycle, but due to its feedback circuit, that is most common fault in the power supplies, this resistor is devalued. Its resistance is slightly increased, because it is high current component, it is in 2 watt, 3 watt. Sometime due to overheat condition, because it is dissipating power all the time, its contacts are bad soldering, that will increase its contact resistance. If contact resistance is increased 0.75 ohms resistor value, if contact resistance is increased, might be it is 2 ohms, that time it will produce this error. That is not a fault due to component, might be due to bad soldering, might be due to its devaluation, anything that will cause to increase this peak. If these peaks without load are high, this IC will not provide full required current. That means if this power supply is for 70 watt, it will provide just only 20 watt, 30 watt. At 30 watt, its output will not increase. I sense signal, that is from this resistor, then current sense feedback components, that is this resistor connected at pin number 3, and this capacitor. Anytime this zone is problematic, this power supply will not provide required power. These are the basic parameters to take maximum output. VCC voltage at no load, at full load. Duty cycle at no load minimum, full load maximum. Current sense signal at no load minimum, full load maximum 1 volt peak. If there is abnormal sound, first might be the winding is loose. That time we can take varnish, liquid varnish in syringe, and we will inject in the transformer. Might be core halves. If the core is separated, its epoxy is loose, that time it will create sound. In some cases there is gap between bobbin and core, that time we can inject any epoxy to fix this core and bobbin together. If switching frequency is out of limit, that time this transformer will create sound. If there is any capacitor short circuit in the output area, that is leak, that time it will create hum sound. Then abnormal heat in the transformer, most probable cause switching frequency. If switching frequency is less or more, it will saturate the core, because high frequency switching transformer needs a specific frequency. If magnetizing current will increase, that time it will reach in saturation, so it will become heat up. Then there is other possible reason, that is RCD snubber. Then abnormal heat of MOSFET. If MOSFET is heating more and more, possible reason RDS on. If you are replacing MOSFET, might be its RDS on, its on state resistance is not matching with the engineered model. That time we need to check the exact part number that is required for this board. Then RCD snubber, that is to demagnetize the core and to remove stress from this MOSFET. Gate drive components, its charging discharging resistor or gate resistance and bleed resistor. If these are bad, this MOSFET will heat up. Then output ripples. If there are more ripples in output, might be this capacitor is bad. Sometime there is RC snubber for rectifier, that is bad, that is connected across this Schottky rectifier for fast recovery. For high frequency switching applications, that RC snubber is bad, this RCD snubber. If you find live voltage in chassis, most of the time class Y capacitor is damaged, that is connected between line and chassis, neutral and chassis, that causes live voltage in chassis. Live component in output in secondary side. This live voltage in chassis, that is due to these two capacitors. That are these two capacitors. These are connected between line and ground, that is chassis ground. neutral and chassis ground. And this fault, live component, live voltage in output side, secondary side, that is due to this capacitor, class Y capacitor, that is connected between primary ground and secondary ground, class Y capacitor. That is for common mode noises in the secondary side. The second possible reason that transformer winding is crossed. Primary winding have physical touch, physical connection with the secondary winding. Then there is a possible fault, SMPS not starts. That is due to most of the time soft start circuit, that are these components. When this soft start circuit is turned on, it will pull down the reference voltage. That time this IC will not start up. And second possible reason, IC. Third possible reason, VCC voltage are not in limit. These are possible reasons for not starting up. Sometime there is another condition, the output starts linearly. That time this circuit is involved in that fault, soft start circuit. Let's suppose this circuit will provide 0.1 millisecond to produce delay time. If it is providing more delay, that time this IC will increase its duty cycle to provide output linearly. These are the possible failures and possible faults and their troubleshooting. If you have any other experience other than this, please write in the comments. I hope you enjoyed this video. If it is good, give a thumb up. If you have any question, please write in the comments. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.